Good day, everyone. Thanks for joining the MIPI webinar, MIPI Debug for I3C, the next generation debug interface. Today's webinar is presented by Enrico Carrieri from Intel Corporation. Enrico is also the chair of the MIPI Debug Working Group. Today, Matthew Schnur, a debug architect at Intel Corporation, is also joining Enrico. A few things to note before we start off. The session will be available on demand approximately 2 hours after the end time of the session. The presentation slides are also available on the MIPI Alliance website in the Knowledge Library at mipi.org. The presentation is around 30 minutes and will then go into a Q&A session. Currently, you're viewing the webinar console. You can minimize and maximize each of the console panes by simply clicking one time. I encourage you to raise your questions in the Q&A pane, and we'll try to get to all of them during our Q&A session today. So with that, I would like to introduce Enrico. Thank you.
So I'm going to talk a little bit about the debug working group inside of MIPI Alliance and give you an idea of the things that we do. And then we'll move into the main presentation around the debug for I3C. We'll talk on the problem statement and goals and why we're doing debug for I3C. We'll talk about the basic principles of that specification. And then we'll get into more of the nitty-gritty, the supported network adapters, and some of the pieces inside that specification. We'll wrap it up with a summary and conclusions that I hope you all get from this, and then we'll get to the questions and answers at the end. So let's get started. So on the debug working group. So the debug working group is one of the many working groups inside the MIPI Alliance. And as you can see here on the slide, the work group focuses on developing specifications and documents in order to reduce development cost and to improve time to market through those various focus areas that are listed there. We focus on debug and trace interfaces and protocols for various different systems across all the things that MIPI focuses on. Now this is a pretty busy diagram here, but what it's trying to show is our specifications and our other documentation that we have range across the whole system, right? And that diagram is showing that whole system there. The different clouds that are throughout that diagram represent the different specifications or our other documentation, and they're pointing to different aspects in that whole system. At the bottom, there's the actual debugging tool, which we call the debug and test system, or DTS. And as you go up, you'll enter into the target system, or TS. That's going to be debugged. And you'll start there at the interfaces and the PCB, through the debug hardware, all the way up to the software that's running on top. You can see all those different places that we cover. The working group in its specifications and documents cover a great amount all the way from top to bottom. And so here we're going to focus on one of them, which is the debug for I3C. So let's talk about the problem statement and goals for this. So the problem statement is really, when we were looking at this, that our current debug interfaces that we have, your traditional JTAG or UART, are really falling short of today's new requirements and use cases. Okay? And you can see here I have a system that it's just an example system where you have maybe an application processor with a modem and a PMIC that has a Type-C receptacle here. Let's see. So we want to be able to debug all of the different components that are on the system there. So you want to be able to not only debug the application processor, but you want to also debug the modem and the PMIC. And here you have that single connection that you can see there that goes between them all and connecting to the receptacle. So you want to be able to do that. Now, you also want to be able to attach that DTS, that debug and test system. You want to be able to not only connect it to those pins like you normally would, but you also want to do it maybe from the modem. So for example, maybe you're out in the field and you're not going to connect directly. You want to go through the modem and you want to go through that network. You should be able to do that to then go and debug maybe the application processor. Or maybe you're on the system. Maybe you're running software on the application processor and you want to debug maybe the modem or the PMIC. You should be able to do that through that same connection that you have, that same connection between those devices. The other thing, as we all know, things get powered down, right? So maybe the modem stays alive and the application processor goes down, right? So you also want to be able to still debug that scenario because, as we know, low power scenarios are really getting more and more complicated as things go, and you want to be able to debug all of that. So I still want to be able to come through that receptacle and debug that modem even though the application processor may be down. And maybe I want to have it come back up and debug that when it comes back up. So these are all various different things that make things a little more complicated now that maybe your JTAG or your UART or your historical connections may not be able to do. And that's what we were trying to focus on here. Now, the end goal is kind of what we were saying. We wanted a scalable, multi-mastering interface that I can connect to multiple different pieces on that platform, different components on that platform. And those platform components are power managed. They can come up and down on the network. Right? And a couple things with that. So I need it to be a minimal set of pins. Right? I don't need 500 different pins. I need two pins. Right? And that includes even interrupts. Right? So if I have different interrupts, I need that to be in band. I need that on those two wires, minimal set. Again, need that multi-component connectivity. So those two wires go to everywhere. Then I should be able to connect to all of them just using that same two wires. The multiple entry and mastering points, again, I should be able to come through a receptacle or through the application processor, whatever it may be. I should be able to come through those and master from those points and then debug the other components. Great thing is it should be flexible across the platform's lifecycle. So again, maybe in your lab manufacturing environment, I come through pins. But maybe in that production environment in field, I come through that modem. I should be able to do that and be flexible when that happens. And again, back to the power down of a component, it shouldn't break the network. That component, if that like application processor goes down, I still should be able to do things. And it needs to be able to rejoin as well. So again, when it comes back up, I should be able to start debugging it all over again. Okay. So now let's talk about the actual principles, what we actually are doing as part of debug for I3C. So the foundation, the main piece that we build upon is the MIPI I3C specification. And we chose that because it has a lot of the features that really hit those goals that we want. It addresses those concerns and those problems that we saw with those older interfaces. So I3C, if you're not familiar with it, it is a multi-drop two-wire interface, exactly what we wanted. And it supports those multiple masters, and it supports what they call hot joining, or when the system goes down and comes back up, it connects again back to the network. So it hits a lot of those main points just right there basically. Right? No major changes there at all. And it supports up to 12.5 megahertz, and it has many different high rate modes. Now, it uses this master to target communication method. So you have someone that's mastering or initiating transactions, and it's going to a target to go do something on that target. And I can support multiple masters, and I have ways to hand off that bus, those two wires, to those different multiple masters, so not beating up each other trying to talk to a target or sets of targets. And I think I mentioned this a little earlier about in-band interrupts. That's something very important. That is part of I3C. It has that support for in-band interrupts, and that gives us the communication back from the target to the master. So not only can the master go to the target, but vice versa through those in-band interrupts. And for debug, those in-band interrupts are quite important. We're able to indicate things like a change in state, or maybe we're collecting some trace information and we want to indicate back to the DTS, hey, I hit a threshold, you may want to come get the data, those kinds of things. So a little note on the I3C specification, as you may or may not know, there are two kind of versions here that the debug for I3C is actually can be built upon. There's the MIPI I3C Basic, which is publicly available, or the standard MIPI I3C 1.0 or 1.1. And though all of those can be a foundation, it's not exclusive to any. You can build your solution, your debug for I3C solution on top of any of those specifications, okay? Including even the first one, the 1.0, where it's compliant on any of those, okay? So that's the foundation. Now, what did we do on top of that? What did our debug for I3C extend? Okay, so we take that MIPI I3C specification, and now we're extending it, and we're adding additional capabilities that are permitted by the I3C spec. And we call these kind of things these extensions, okay? So again, we're going to utilize all the features I3C gives us. So it gives us the 2 wires, the hot join, the IBI, multi-drop, broadcast messaging, all of it. We utilize and can utilize all those different features that are in I3C. But what we do is we take those CCCs, or common command codes, and we define a few specific ones for debug. So we have some specific CCCs for configuration, function selection, if you're going to do like trace or something, and we can do what we call these action or event triggers and interrupts going back and forth between that master or the DTS and the target. Beyond just the commands, we also add specific mandatory data byte values for the IBIs. And that's really to indicate special things for debug. Maybe it's a debug status change, or maybe there's a debug error or something like that. We can indicate that specifically for debug by having those specific MDB values. And one of the other things that we do is we standardize this data exchange, okay? So you have these private transfers, right? Your read and write private transfers. And as some people call it, there's usually this contract that's between a master and a target. And what we do here in debug for I3C is we actually standardize what that contract is for debug. And so we connect the debug host, or the DTS, to that port. And we have these predefined network adapters. And if you're familiar with any of the debug specifications, there are many different network adapters. And Matthew will get into those a little later, all the different network adapters. But we have these different network adapters that do trace or debug communication and things like that. And we define how that data exchange is going to happen, or that private contract that's going to happen. And so we define those. On top of all of that, some specific features that we have inside the debug for I3C is that we allow the ability to have a dedicated debug topology, so you can use that I3C specifically only for debug, or if you're trying to save wires, you can share that with other functions. So it can be debug and non-debug shared. And again, having special CCCs, MDBI, for IBIs, we can differentiate what's going to be used for debug and what's going to be used for non-debug. We're able to handle that. Our debug communication is byte-oriented, just like the debug for I3C. It's kind of what we call it a streaming interface. That's byte-oriented, and it's various different protocols. And again, Matthew's going to talk about all those different protocols that we support as part of our network adapters. Now, we talked a little bit about those network adapters. The target system can expose more than one. It's not limited to just one. We can have multiple different network adapters or interfaces or ports. So, for example, with that single connection, I can do communication and configuration and status, and I can do trace together in that one interface, which is quite powerful. I am also able, as part of the DTS or the master side, I can broadcast or send directed requests. So I can say, maybe back to the example in the beginning with the application processor, I can send a specific directed action to it and say halt or reset. But I can also, if I wanted to, tell both the application processor and the modem, both of you do a halt or a reset. I can broadcast it to everything on the network as well. So I can do both. And then the last is, I think we've talked about, there's those in-band interrupts, and we can use those in-band interrupts for triggers. So maybe I need something from one to trigger something else outside of it. Or I can send different requests. Maybe, hey, data's waiting, come get it. Right? I can send those different requests back to the DTS in that case. So this slide has a lot of different conceptual diagrams of this, what we're doing inside the specification. So let's focus first here on the left. So on the left is a traditional, what we call our layering diagram. And if you're, again, used to any of our debug specifications, you'll see this diagram. We kind of call it the butterfly diagram. And it shows on the left the DTS and its stack. And then on the right is the TS and its stack. And you can see there's different layers that all kind of match up as you go up. And you can see at the bottom there's the I3C link and the transport. And then there in the middle is that network adapter. And that's really what the debug for I3C specification is really focused on, is that network adapter and how it connects to the I3C transport and above to the various debug functions. Okay. Now, as we move over to the right is just a more in-depth look at those functions. And you can, again, see the different pieces and how they link up. Okay. So the next part of this is really going to dive into those different aspects and what's actually going to happen here and that. One of the nice things about these diagrams, especially the one on the left, and again, if you're familiar with the debug specifications, it's very common to see a lot of different layers that are going to be the same. You can see, and Matthew will talk a little bit again about those network adapters, and you'll see those are very common for other interfaces. And so you'll see how we layered on top of that, very similar to some of the other specifications that debug has. So at this point, Matthew's going to take us from this slide and going to talk more about that functional diagram, dive into that, and give you some more information. Matthew?
Thanks, Enrico. So moving into the conceptual target system diagram here, we see the network adapter really as a collection of FIFOs for traffic going inbound into the debug function, traffic coming outbound out of the debug function, and eventually into the I3C bus to be consumed by the DTS, the debug test system. And we see some common logic in the middle, which really talk about the extension layer. And this really talks to session management, and specifically a session management state machine that deals with bringing this part of the network function into a running state, into a stop state, and dealing with the transitions between them. So it really depends on the type of work that's going to be done here and the type of debug. But you could have one or multiple different network adapters in here, and they could be different instances of the same type of network adapter. They could be different instances of different types of these things. And the purpose of these could really vary depending on, what sort of debug functions are being done. For example, they could be optimized for a different type of thing. For example, getting to an internal tap network, reading or writing different debug registers, consuming data as part of a read-only or an outbound-only implementation that deals with trace infrastructure. And depending on what you need for the sort of debug functionality that a chip needs, you could basically mix and match and include the sort of things that need to be included for whatever needs to be done. But the common layer, which is the things on top of the transport layer and the pink box in the middle for the network adapter, this is what debug for I3C really defines. And this, I think, is the value for what we are really bringing to I3C here to enable what the debug function needs to be. We also see the debug extensions on the bottom yellow box here, which is the I3C network layer. We see two CCCs, and they're pretty small. You may not be able to see them here. We see one called debug action, and these are the debug actions that Enrico talked about earlier. These are the broadcaster direct actions that you could send to one or all of the debug devices on the bus. And we see the debug opcodes, which are the ones that talk to putting data into and getting data out of the various FIFOs, the operable parts of the state machine, the version, the status, the things that you use for discovery and, bringing this thing up, configuring it, get it working on the bus. These are the kind of mechanics and nuts and bolts of getting debug for I3C working. So moving to the next slide here, I touched on these earlier. We have two different CCCs, one called debug opcode. We talked briefly about this one here. These are the things that talk about the network adapter. That's the pink box we talked about earlier. This is reading the debug capabilities, configuring the network adapter, getting the session machine into the right state, controlling the FIFOs, making sure they don't, overrun or underrun, making sure you know what size they are. And we have debug action, which is the direct and broadcast version of the CCCs that talk about, things like halt, things like run, and also room for other vendor or implementer specific actions that implementers may want to put in there. There's a space for a vendor specific range that's interesting that people could do whatever they want to with. But the mechanics and the process for getting those things in there is the same. Start trace is another interesting function here that you could use for debug action as a direct or even a broadcast. And that means that you could have a single broadcast out here that says start trace that could just tell all the devices on the bus, start now. We have the inbound interrupts. We talked about these earlier. And using mandatory data bytes, which I3C 1.0, I think, defined at some level, and I3C 1.1 defines even better, we actually requested and received 3 specific values in the range of mandatory data bytes. These are the first bytes as part of the data payload in the inbound interrupt through I3C. And with these specific values, you could actually program the master of the I3C bus to respond automatically. For example, you've got a change in status. You need to handle something right away. You've met or exceeded a FIFO threshold. A session stopped, a processor halted, perhaps even something needs to be handled right away. You've got one for debug error. This is an error condition. Something went very wrong. You need to take care of this immediately. And you've got debug data ready. This one indicates that there's something to be read. And depending on the type of the I3C master you have, you could even program this one to immediately follow that up with a read. And that one says, just go ahead and read this data. I've got it ready for you right now. The next read you do on the bus is just going to pull that data. And that's something the debug for I3C specification defines, which is as soon as it issues that IBI with the MDB value here, I have that data ready for you to read immediately. It was a private contract, and then we actually kind of made that a public contract called a pending read notification. This means the data is ready immediately. So as soon as that inbound interrupt is issued, the data is ready, the master can read the data. That's a pretty powerful feature. The various types of supported network adapters, again, they're going to change depending upon the types of debug operations you need to do. But usually you could have an inbound data pipe, an outbound data pipe, or both. And these are tied very much to the types of private read or private write requests. If you're in I3C and you're doing things through SDR mode, for example, just writing straight to the dynamic address of the device or reading straight from it is directly linked up with the data pipe. And those are what the FIFOs and buffers in that pink box that we saw earlier are linked to. This is how we communicate with the debug functions within the target system, and specifically with this particular piece of silicon. And each one of these is mapped to a debug function with a particular protocol. And the implementer gets to choose which one of these there are. And you can have up to 16 instances. They don't all have to be uniquely typed from each other. You could have multiple of the same. You could have individual ones be different. And for example, we've got one here called Sneak Peek, and this is a lightweight version of Sneak Peek that was defined earlier by the same working group here. And this one basically has bidirectional transfer of blocks of bytes, and this is used for kind of command and control. We can think of this as a way to basically send commands and get responses to debug logic that's above the level of this network adapter. We've got Trace Wrapper Protocol, or TWP. This one's used for getting trace output. We think of this one as a unidirectional flow, which has an outbound pipe only. We've also got System Trace Protocol, which is a different type of trace protocol, again, unidirectional, outbound only. And this one's kind of meant more for system trace macro cells. And we see a lot of software debug flows that use this one. We've got Simplified Address Mapped Protocol. This one we see used more for simple address mapped accesses to TS resources. And the area in which I think this one's going to shine well is lightweight access to things like debug registers or other internal registers, where you just need to do simple reads or simple writes of registers or memory ranges. This one could work very well for that. We've got classic UART. We've got things that work well for things like software-oriented agents like scanf or printf, GDB monitors. It's bidirectional because that's what UARTs do. And we've also got space for implementer-defined things. We don't know what everybody's going to need for these things, and if somebody has something that doesn't fit neatly into one of these types of network adapters, they have the freedom to make something else of their own. So as an example, we've got kind of the one of everything approach here. Somebody has picked, one of each of the things from this smorgasbord, put it into a piece of silicon, and each one of these has a unique index. That's the one thing that's needed. They each have to have an index. And then the debug specific handling over here on the bottom, which is the debug opcode, the debug action CCCs, the handling for those, and then the upstream connections to the debug functionality here. So the point here is that MIPI I3C gives us the scalable interface, and especially the multi-mastering interface, because as we saw in the platform diagram earlier, it really isn't restricted to which particular piece of silicon or which particular input-output method is being used to connect to this I3C bus, because you could do it many different ways. And the point of this is that power management is supposed to be expected in this. It's not like we're routing this thing through a single chip that is able to command and control every specific piece on here. You could have any one of these things do this with I3C's multi-mastering capability. You could do this thing. And this meets a lot of new requirements that a lot of the legacy interfaces simply couldn't do. And we basically were able to extend I3C as a bus and as a protocol and make it usable for debug. And we take advantage of all the features of I3C, including the two-wire bus, the ability for devices to hot join, in other words, to come up from a powered off state safely, announce their presence on the bus, wait for the current master to acknowledge them, assign an address, send interrupts to tell their status of interesting and possibly error conditions, to be able to send broadcasts to multiple addresses and pass mastership back and forth at the right time, and take advantage of the ability to extend with CCCs and other things that are specific to debug and exchange data the way that we need to do to use it for debug. So we've got a couple links here that talk about more information. Of course, MIPI's website is on here. We've got the Debug Working Group public page here that talks about all the debug specifications that are available publicly. We've got an architecture overview for debug that talks about kind of the general architecture and how things are expected to be laid out. We've got I3C as a specification, which started out for sensors and is now being extended to all sorts of other domains, including debug. And then we've got debug for I3C as a specification linked here, which can be downloaded now because it's publicly available. And we want to kind of present this to the world and see this be used, see this be useful, and eventually see this be extended and grown into new opportunities and new use cases that take it even further. Enrico?
Thanks, Matthew. I think one other thing to note is back on those on the previous slide with the MIPI specifications, you can find some of the specifications about those network adapters that Matthew talked about. Those are also there. You can download those as well as part of the Debug Working Group page, just to let you know. And with that, I think we're ready for questions.
Thanks, Enrico, and thanks, Matthew. That was great. Appreciate that presentation. So I encourage the audience to pose your questions in the Q&A pane. We'll go into our live segment now, and I do see that there are some questions that have come through already. First question is, can I also add I2C devices on a bus supporting debug for I3C?
With some limitations, yes. Typical I2C slave or target devices can be added on an I3C bus, but I2C devices that can act as masters on the bus cannot be supported on any I3C bus, and that applies to I3C debug as well.
Thanks, Matthew. Appreciate that. Next question. Can I use the same sneak peek engine and logic that I have with my gigabit debug implementation for debug for I3C?
So the simple answer to that is yes. There is a little bit of complexity there. Sneak peek is that debug protocol that, as Matthew showed in the slides, it's one of the network adapters. And the idea actually is part of how the debug workgroup did it. And if you remember that picture in the very beginning, we do these different layers. And yes, the idea is you're able to reuse that sneak peek engine. Now, one slight difference is because debug for I3C is definitely at a lower speed than some of those gigabit debug like USB and such, there is a different format for sneak peek. So the sneak peek specification defines two formats. They're traditional, or what they now call the full SPP, which was used with the gigabit debug for USB or for the Internet Protocol sockets. And then there's a tiny version of it to really optimize the messaging for something like an I3C bus, where you don't necessarily have that bandwidth that you have with like USB. So the format is slightly different. So things are maybe smaller and things like that, but the behaviors and everything of that engine is still the same. So there is reuse between what you might have done in your sneak peek engine for gigabit debug and what you can still use for debug for I3C.
Thanks, Enrico. Next question. How do I get I3C on a standard PC as a DTS?
There is a separate effort that's being run through the USB Implementers Forum as part of the device working group to develop a standard device class specification for USB I3C devices. Companies who are members of the USB Implementers Forum who are interested in that should join that effort and help to develop that as a standard, and that will help to bring that to standard PCs or other devices as well.
Yeah, and that was something that, yeah, I was going to say one thing to add to that. I think, Matthew, that was something that MIPI definitely supports that effort going, that they're doing as well.
Okay, very good. Is there any relationship between I3C and I2C?
Yes, I3C was actually developed to be backwards compatible to some degree, and we talked earlier about I2C slave or target devices, and the standard communication in what's called single data rate or SDR mode for I3C is very much based on the standard transfers in I2C. So it is inspired by and actually very much compatible with I2C in that regard. And again, some devices can coexist on an I3C bus. So, but again, I3C was largely developed to move beyond move beyond I2C and increase the data rates and also add things like inbound interrupts and multiple masters with control over passing mastership between them. So there is very much a relationship as far as lineage and descending, but it actually takes things much further.
Okay. Next question, which performance can be achieved for debugging and trace?
That's a really good question. I think that, and I see a few other questions around kind of the same kind of thing, and there was a question around the trace. So the performance is, there's a lot of different factors. There's the factor of what I3C natively can do, and then what your trace or your infrastructure connecting to the I3C controller can do. So I think that the second part of it is whatever your system can handle. I think that that's under the control of your implementation. But let's talk about the I3C side. So I3C supports, as I was mentioning earlier in the slides, a 12.5 megahertz clock. And there are several different data rates that I3C supports. So we have a single data rate, so that gives you the 12.5 megabits per second kind of transfer. You also have your dual data rates and other data rates that are in there. So the Debug for I3C specification supports any of those higher data rates. And there's several of them. There's several that are just data rate specific. There are also ones where you can use additional lanes. So all of those are supported. So you're able to scale to those values. Again, it's that's going to be the limitation on the I3C side. Now, do keep in mind, for something like Sneak Peek, you're going to have some overhead because of the Sneak Peek protocol. So let's just take a single data rate node where it's 12.5 megabits per second. You're going to lose some of it based on what you're going to do. So it's not going to be 12.5. It may be 10 or 8, depending on what the kinds of messages that you're sending. So you will lose a little overhead there. Same thing with trace. If you use something like STP or some other one of the other or TWP or whatever for MIPI, again, you'll lose some to the overhead. And again, that's your limitation on the I3C side, and you'll need to make sure that your implementation internally can then not starve those interfaces. Now, is that slow? Well, if you're looking at something like trace, it could be very slow. We're not claiming that I3C is the highest and fastest and best. And it kind of goes back to the question of reusing things like Sneak Peek Engine and such from Gigabit Debug. The idea is that the way MIPI does their specifications, we're able to go between these different interfaces using the same kind of protocol layers like Sneak Peek, like STP. And so, yes, maybe it's not high bandwidth, but I am able to switch between the different interfaces when I need to. And something like USB, where you may have that with a Gigabit Debug interface, that may not be available to you at all times. And that was one of the focus areas with I3C, with having it work in those low power scenarios on your platform. So with the question of, is this fast enough for something like trace, it really depends. You can get simple messaging out, right? Simple messaging works pretty decent with this, but it really comes to those different scenarios. Maybe that's good enough for when you're in those lower power scenarios. So it's just things to keep in mind. And again, the Debug for I3C is part of the larger architecture that MIPI provides for maybe a more complete solution, right? If you want both the low power, lower bandwidth, always available, bare metal like I3C, and maybe your higher speed, higher bandwidth, like what you would get out of Gigabit Debug. Hopefully that answered a couple different questions that are kind of related to performance.
Thanks, Enrico. Next question, are there any security features in the protocols?
That is a really great question. And today, there is not. So right now at this stage, the idea is you would utilize your security features that an ASIC or an SSC is implementing already for their debug. Now, I will say there is an effort going on. It's an ongoing effort to actually look at security features in the protocols. That is something that's active. Those who are contributing members can definitely get involved in those discussions and how that's happening. But those are ongoing, and there is a good amount of effort going on. You may know that MIPI as a whole is looking at security, and they have an investigation group going on looking at security, not just for debug, but across the board. So there is ongoing efforts there, and look for them coming soon, hopefully. But yes, there's efforts, and I do encourage those who are contributing members to MIPI to definitely get involved if that's important, and provide your feedback and ideas.
Thanks, Enrico. Next question, is this a purely mobile handset focused technology?
Absolutely, 100% no. You can use I3C in many different areas, and as MIPI calls it, it's the Beyond Mobile. So this can be used in various different platform types. MIPI has we have a focus on things like IoT, automotive. It can work in lots of different scenarios. As I mentioned a little earlier, I3C is it's good for those low power, always on kind of connections. And as I mentioned in the very beginning, this is one of those where we were considering something better than maybe your traditional JTAG or UART, right? Where you would maybe use those technologies before. Here we're saying you may want to start looking at I3C and see what you can get better, and hopefully we are looking at more requirements that are necessary with our newer technologies. But no, there's no limitation on the solution here that we're talking about in the specification to just mobile. No, that's not the idea. And in fact, I'll be honest, there's no limitations like that on any of the debug. The debug interfaces and all of the debug specifications that we have are for any different platform that you may have. It's not specific to mobile. But again, it really depends on your situation and where you may use, like I said, use these older technologies like JTAG or UART or whatnot, and where I3C can come in and actually hopefully be a better solution in those areas.
Thanks. I do see we have a few more questions, so I will go through those. Isn't the 12 megahertz bus speed kind of slow for trace?
Yeah, I mean, as I mentioned a little earlier on the speeds and performance, yes. In most cases, it's probably a little slow. But again, if you step back and look at it from a complete solution, right? If you may have I3C as that, I like calling it maybe your JTAG replacement, and utilize that for your low power transactions. Maybe 12 megahertz or let's look at even a DDR data, the dual data rate where you get probably 18 to 20-ish, assuming there's, with the overhead, 18 to 20-ish megabits per second. Yeah, you're not going to get huge amounts, but maybe that's okay. Maybe that's all you need in these lower power scenarios where maybe my gigabit debug isn't available because I don't want to disturb the system. So we felt that there are certain use cases where having some trace was still useful. Now, also keep in mind, because of the way we do layering and how you can take your trace ecosystem that may be built off of the MIPI specifications like STP, you can take that same, let's say, output from your aggregation and not only send it to I3C, but you can send it to those gigabit debug interfaces like USB. So with the same ecosystem, with the same system that you have, you can utilize those two different interfaces and maybe switch between when you're in that, like I said, that low power scenario versus that higher power scenario. So maybe, again, back to is it fast enough? Maybe not in all situations, but because of the way the specifications are written and how you can implement it, you may have this nice ease of going back and forth based on the scenario, what you're actually tracing and whatnot. So again, it's in some cases it's slow, absolutely. In other cases, when we looked at it, we said, that could be quite useful in those scenarios. Hopefully that answered it. But think of it from a whole system approach where, like I said, you can do that interchanging, and think of it as when you have a bare metal interface, when you have that lower power interface when things are going down and such, something is better than nothing at times. And when you're looking at it from a potential, like a JTAG, like a JTAG replacement, I3C is definitely going to do you better than JTAG in that regard, because again, the way it's architected is it should fall real nice into your existing trace ecosystem.
Thanks. What about debugging of targets which are alive for very short periods of time? Registering on I3C bus may take a longer amount of time?
So this one, we actually could take advantage of I3C's hot join capability. And I think it really depends on the I3C controller that's being put into the target device. If it's able to, well, I think this actually depends on how this is implemented, because if the master is able to respond quickly enough and assign it an address quickly enough, I think you can actually make use of this. It's going to depend on the specific implementation. So perhaps this is something we can address in a follow-up session more directly, but I think there is still a possibility to make use of this. It depends on how long very short is. Go ahead.
Yeah, and it also depends on how you may partition your logic. So for example, if you're able to maybe retain the dynamic address of the target, then, like Matthew said, getting back onto the network is very simple, right? I think what may cause the delays in when you come back up is potentially reassigning the dynamic address and any other configurations. So if you have a way to retain that, then you can probably be very, very quick, and then it won't necessarily matter. And again, like Matthew said, it also depends on what your exit latency and whatnot is coming out of those lower states. So it's a little bit of a mix, but there are definitely ways to handle that. It really just depends on the different circumstances and what you can actually do with your ASIC. And if, like I said, if you can do something like retention and such.
Okay. How easy is it to get started with debug for I3C? How do you recommend getting started?
So what I would suggest is first making sure that you have a decent foundation with I3C. So I personally would go, and I think MIPI has a little bit ago, we had a webinar on I3C. So if you're not familiar with I3C, I think that would be good to have a good foundation there. The other thing to do is get the specifications, as Matthew said, is available on MIPI's website, both the I3C and the debug specifications. So definitely, absolutely take a moment and download those, start reading those. I think that's really where you want to go. As I mentioned in the beginning, the debug for I3C works with any of the I3C specifications. The I3C 1.0, I3C 1.1, I3C Basic 1.0. It works with any of those. So whatever you want to start with is great. And that also means you can take existing IP that is out there. So if you have a master controller and a target controller that's compliant with any of those specs, which means any controller, you can start with that and start getting those to work together, and then slowly add in those different CCCs and connecting up. One of the things, at least from a debug for I3C, that you'll need to decide on is what network adapter you want to put in there. And there's some different considerations for network adapters. And in the annex, in the debug for I3C, there's a comparison chart and some additional help on how to select those. So for example, you typically will want something to do debug communication, where you want to send in some commands or read some registers and whatnot. And there are different network adapters that do different things, everything from the very complex and fully featured sneak peek all the way down to something simple like maybe a virtual UART in a way. And so we have a table that really shows how these different solutions, the pros and cons of those different network adapters for those things. So I would suggest, once you get a little familiar with the behavior between the controllers, which, if you get some IP, you probably will be able to put that in maybe an FPGA or something to play with. Look at the information on the network adapters in that annex to help you figure out what that next step is in getting the network adapter. Like I said, you can do something very simple like a virtual UART, which is explained in the specification, or simple address data mappings on an internal fabric, which is also mentioned in there. It's called the Simple Address Map, or SAM controller. So there's some very, very simple controllers that can get you started doing very simple peek and pokes and things like that from a debug perspective that is probably done very easly in an FPGA to play with and get familiar with. And then build up into, depending on what you need, up into those sneak peek engines, where you can get way more fully featured capabilities.
Great, thanks. Is there any advantage over just chaining everything into a JTAG ring?
Absolutely, absolutely. So as you know with JTAG chains, hopefully, if one of the devices is busted or powers down on that chain, your chain's broken, unless you do other things to get around it, right? And people have done things. I've seen implementations where you have kind of a leapfrog kind of logic or things on the board to get around that. In I3C, you don't have that. You don't have that chain. It's a network. And so when something does fall off the network because it's busted or it's powered down, there's still the remaining part of the network is still there. It also helps with how you do some of the routing, and so you have those capabilities. The other thing that I like, and maybe it's not exactly to your question, but the other thing to keep in mind too, with JTAG, everything has a particular flow. You have kind of a master that then goes through the chain, right? A single entry exit point, right? Whereas I3C doesn't. So you do have multiple masters, as you know, as we said. So the thing that's nice there, again, it's back to if one of the components goes down or is busted or whatnot, especially since you're in debug, right? You should expect some, you know, maybe one of the problems you're debugging is something is busted on your network, right? I'm able to recover better because I have multi-mastering, multi-target kind of interface, whereas JTAG is that single chain. So, Matthew, I don't know if there's anything else that you want to add to that, but that's my feeling on why it's better than JTAG. And I could probably spend a lot more time, but
that sums it up nicely.
Hopefully that answered the question.
Thanks, Enrico. I'm mindful of the time. We have just a few more minutes left. I think I could probably squeeze one more in. What is the time frame for implementation? When do you think debug for I3C will be widely available?
Oh, that's a great question. That's a really good question. This is, well, as you know, we just came out with it. So it's going to take a little bit of time. I think one of the things that the debug workgroup really started to consider was what we use the term adoption aids. What can we do to promote and make that maybe time to market quicker? Matthew did talk about one of the efforts that MIPI did maybe promote is the I3C device class as part of the USB IF. And that was something I think we answered. There was a question earlier. We were pushing that to help make sure that there were ways to get from standard PCs and your standard USBs that people use today in debug to then be able to create the tooling necessary to connect to I3C, where you can connect it. And I think someone was asking about how do you connect potentially on the board. You know, one of the things in our mind was to have your standard laptop or computer or whatnot PC connected to this USB to I3C device based on the I3C device class. Then that would connect to maybe a USB type C connection where I can then connect this all up. So we have been thinking through those. You may see more from the debug workgroup to help people understand these kinds of developments. MIPI will be continuing to try to promote and push other things to help with that kind of stuff. But it is something that we've been trying to consider to how to promote and accelerate these things. So it's probably not a great answer to your question. It's not something we really know, but we have spent some time, and why we did this webinar as well, why the work group is spending time thinking about these adoption aids and what we can do to promote.
Well, thanks, Enrico, and thanks, Matthew. That was a great presentation, and thanks to everyone for tuning in and asking these great questions. I would like to just reiterate that this is available on demand, and you can also find the slides at the MIPI.org website. You'll also find other information related to debug and I3C. And we hope that you enjoyed this session. Thanks again, everyone, for joining.